So yeah, I'm going to be giving a talk about how we can use econometrics to analyze human decisions and machine predictions. And so rather than trying to give sort of a usual economics style seminar talk crammed in 20 minutes, I thought I would try to cover two papers that I think are related to each other and try to tackle a similar problem from different perspectives. So as Dan said, let me start with some motivation for some problems that I've been thinking about. So in many high-stakes settings, expert decision makers must make really consequential decisions based on the prediction of an unknown outcome. And these settings are really ubiquitous throughout society, so let me just start with a few examples. First, in the criminal justice system, judges decide which defendants should be released prior to their trial based on a prediction of whether they would fail to appear in court. In the healthcare system, doctors decide which patients should be diagnosed or tested based on a prediction of whether they suffer from some underlying medical condition. And then as one last example for now, in the labor market, managers decide which job applicants should be interviewed or hired based in part on predictions of their on-the-job productivity. Now, across all of these domains, and many others that we can come up with, computer scientists, data scientists, and policymakers are actively designing and implementing data-driven algorithms that are trained on historical data to make predictions to, in turn, inform or replace these decision makers in all of these settings. Now, to me, this activity raises two very related questions. So the first comes from how can we evaluate the quality of human decisions in these settings in the first place? In other words, do these expert decision makers like doctors, judges, and managers make systematic prediction mistakes based on the available information in these repeated high-stakes environments? If so, which decision makers, on which decisions, and in what ways are their decisions systematically biased? The hope is that by evaluating the quality of expert predictions in these settings, we can help better design these algorithmic tools to improve decisions in the first place. But there's also a question coming in the other direction, which is how do we robustly evaluate these statistical risk assessments and decision rules using data that are generated by human decision makers? So for example, across all of these settings, whether we're constructing predictions of whether a defendant would fail to appear in court, whether a patient has some medical condition or some measure of productivity in the labor market, we face a fundamental missing data or selective labels problem that arises from human decisions. We only observe the outcomes we care about conditional on whether some human decision maker has made a choice. We only observe whether past defendants have failed to appear in court if a judge in fact released them. We only observe a patient's health condition if a doctor decided to test them. And we only observe an applicant's quote unquote productivity if some manager actually decided to hire them. This poses statistical and econometric challenges that we must face, and ignoring them may lead to inaccurate predictions of risk and misleading evaluations of these algorithms in the first place. So what I want to talk about today are two recent papers that I worked on that are related that tries to use classic tools from econometrics to tackle both of these questions and hope make some progress on these problems. So in particular, across both of these papers, you're going to see some tools related to classic revealed preference analysis in econometrics, partial identification analysis, and under the hood of everything are using tools from causal inference. So in particular, one paper I'll talk about is what Dan mentioned, this paper entitled Identifying Prediction Mistakes in Observational Data that I worked on. And then another paper is going to be with some fantastic co-authors of mine at Carnegie Mellon, Amanda Costin and Edward Kennedy, on counterfactual risk assessments. So first, I want to talk about this first paper, Identifying Prediction Mistakes, where I'm going to think about the problem of how do we evaluate humans in these settings in order to better design algorithms. So as I mentioned, it's important to understand the quality of expert predictions in order to design these data-driven algorithms. But this question of whether expert decision makers make systematic prediction mistakes is already at its core a foundational question in economics. And uncovering whether a decision maker like a judge, doctor, or manager makes these quote unquote prediction mistakes in these sorts of high stakes settings, which are far removed from the controlled lab or field experiments that we're used to in behavioral economics, is an incredibly challenging problem for three separate reasons that are related to each other. The first is that these decision makers may observe private information, additional information that is relevant to the decision but unrecorded in the training data that we have. The second is that these decision makers' own preferences over choices and outcomes are unknown to us and may richly vary across decisions. We don't actually know what a judge is optimizing when they're in the courtroom. And then finally, as I mentioned, we, the econometricians or researchers, face a fundamental missing data problem. We only selectively observe the outcome of interest based on the decision maker's choices. So as a result, we face a classically economic or econometric problem, which is when we look at their choices, do they really reflect systematic prediction mistakes in some sense? Or rather, do they reflect optimizing behavior at unknown preferences and information sets? Unknown preferences and perhaps some additional private information. So the goal I had in this paper was to try to ask, can we analyze whether a decision maker like a judge, doctor, or manager is making systematic prediction mistakes under weak assumptions on their preferences and information sets using the sorts of data that we have available when we're designing these algorithmic tools in the first place. So what I do concretely in the paper is I develop an econometric framework rooted in microeconomic theory to try to identify, characterize, and conduct statistical inference on systematic prediction mistakes that can be applied in any of these high-stakes settings. Now, in doing so, I have to clarify what we can and cannot learn from data and empirically relevant assumptions about behavior about these systematic prediction mistakes. But given that we can learn something, take my word for it from now, I'll show that in the paper that we can take data and our assumptions to conduct inference on these systematic prediction mistakes. And then I illustrate, actually I don't know if the clicker works. I show that we can take this framework and apply it to analyze real-world empirical settings. And so I use these results to analyze the New York City pretrial release system and ask whether judges in New York City do indeed make prediction mistakes in their pretrial release decisions. And then finally, in the paper, I try to close the loop, and I'll briefly talk about this at the end, by showing that this sort of econometric analysis of choice behavior can help inform the design of algorithmic decision systems in the first place. And in particular, they can inform this question sometimes called algorithmic triage in computer science about when we should be deferring to or automating existing decision makers with algorithmic decision tools. So to make that all a little more concrete, I'm just going to introduce very, very minimal notation to try to describe the setting I'm thinking about. So in this paper, I'm focused on a setting where there is a single decision maker that makes many decisions. And each decision is going to be summarized by some recorded characteristics that I'll denote by X. So to make that concrete in this pretrial release application that I analyzed in the paper, there the decision maker is a judge who must decide whether to release or detain many defendants. And each defendant is going to be summarized by some recorded information available at the time of the decision, such as their current charge, their entire prior arrest record, as well as possibly some demographic information. Then, in these settings, we, the researchers or data scientists, observe the decision makers selecting a binary choice. So therefore, from the data we observe, we can identify the decision maker's conditional choice probabilities, to again use some language from econometrics. So in this pretrial release setting, this is nothing more than a judge's probability of releasing a defendant as a function of those observable characteristics. Then finally, each decision is also associated with some latent outcome that I'll denote by Y star that the decision maker does not know at the time of their choice. And here, we, the researchers, face what's known as a missing data or selective labels problem. We only get to observe this outcome Y star if the decision maker selects choice C equals 1, for example. So in this pretrial release example, we only observe whether any defendant actually failed to appear in court if the judge that was assigned to them decided to release them. Now, because of this missing data problem, from the data we get to observe, we can only actually identify what is the conditional probability of the outcome, given that the decision maker has selected choices 1 in the characteristics, but not given that they've selected choices 0. So as a result, again, in the language of econometrics, this means that the conditional distribution of this outcome Y star, given the characteristics, is partially identified. We can only learn this object up to a set unless we introduce further assumptions on the problem. So again, going back to that pretrial release example one last time, there in the data, we can only ever observe the failure to appear rate among released defendants, but not among detained defendants. And so the failure to appear rate among all defendants is partially identified. We can't learn that object unless we're willing to introduce further assumptions. So altogether, in these sorts of environments, we're going to get to observe a data set that consists of each decision made by the judge, doctor, or manager. Each decision is going to be summarized by some characteristics X. We get to observe their choice. And if the decision maker selects a particular choice, we'll also observe the outcome we care about. So in this environment, to answer those original questions about systematic prediction mistakes, again, I'm going to use a framework from economic theory and econometrics. I'm going to analyze the decision maker's choices through the lens of a benchmark non-parametric model of subjective expected utility maximization. That is, I'm going to ask, can we explain the decision maker's choices as if they make choices to maximize expected utility given some subjective beliefs about the outcome y star, given those characteristics x, some utility function that depends on the characteristics, choices, and outcomes that are unknown to us, and then any additional distribution of private information, which again, we don't get to observe in this environment. So then to make that question about systematic prediction mistakes more precise, I'm going to ask, can we explain the decision maker's choices at subjective beliefs that are quote unquote accurate? So recall that because of this missing data problem, we can't exactly learn the conditional distribution of y star given x. So I'm going to ask, can we explain their beliefs at any distribution that lies in this identified set? If so, I'll say their beliefs appear to be accurate given the data and given what we're willing to assume in this setting. And if not, I'll conclude that they make systematic prediction mistakes. And if they are making systematic prediction mistakes, perhaps can we go even further and say something about the ways in which their predictions are systematically biased? Do they appear to be biased only over some regions of the characteristic space but not others? And what forms of the bias do we actually observe? So again, I'm not going to walk through all of the sort of technical details in the paper, but just as an advertisement for you to check out if it sounds interesting. So in the paper, what I first show is I provide a complete characterization of whether the decision maker's choices can be rationalized with this model of subjective expected utility maximization at accurate beliefs. Then I show that in order to identify systematic prediction mistakes, we'll need to introduce econometric assumptions to somehow deal with this missing data problem, and behavioral assumptions to restrict the richness of the decision maker's utility function in a precise sense. But under those conditions, we can indeed test for systematic prediction mistakes using quasi-experimental variation to generate informative bounds on the missing data, out-of-sample prediction as an intuitive form of dimension reduction, and then we can do hypothesis testing for systematic prediction mistakes using what's known in econometrics as moment inequality procedures. Then I show that under those same assumptions, we can in fact go even further and analyze the content of the bias in the setting as well. So first, we can bound how common or how costly are these systematic prediction mistakes to the decision maker. How worse off are they at their own preferences due to their own biases? We can bound the extent to which the decision maker's beliefs overreact or underreact to characteristics, to variation in the characteristics. So altogether, these results show that we can answer classic behavioral economics questions in these observational settings. And where I think the paper becomes most interesting to me is that it turns out that these results are useful in practice. So in particular, I go back to this empirical application of pretrial release in New York City and ask whether judges in New York appear to be making systematic prediction mistakes about failure to appear risk in their pretrial release decisions. So applying those earlier econometric results to this live empirical setting, I show that at least 20% of judges make systematic prediction mistakes about failure to appear risk. You cannot rationalize their beliefs as having correct forecasts of failure to appear risk based on defendant characteristics. These systematic prediction mistakes primarily occur on black defendants at the tails of a predicted risk distribution by some machine learning model. And from a behavioral economics perspective, these prediction mistakes arise because judges appear to underreact to variation and failure to appear risk based on defendant characteristics. They appear to be treating black defendants as if they are close to the average in some sense. And then finally, to come back to algorithms in this setting, how are these results useful? How are understanding systematic prediction mistakes useful in practice? In this application, I show that actually understanding which judges and on which decisions they make these systematic prediction mistakes can inform when you would want to automate a decision in the first place. So in particular, I conduct a counterfactual exercise where I show that if we replace judges with an algorithmic decision rule, judges who made these systematic prediction mistakes, we could generate outcomes that dominate the status quo in a precise sense. So hopefully the goal of this paper is to illustrate that classic behavioral and econometric analysis can be informative in this setting. And in particular, they can help us design and understand how we might want to implement these data-driven tools in the first place. So that sort of closes the loop on one paper tackling this first question. how do we evaluate humans. So in the last 5 minutes or so, I want to sort of flip the lens around and ask, how can we use econometrics and statistics to better evaluate algorithms in the first place? So as I mentioned, in all of these settings, we aim to design statistical risk assessments or decision rules to improve outcomes. But we face this core missing data problem. We only observe whether defendants failed to appear if judges decided to release them. We only observe in consumer finance whether past applicants defaulted on loans if some loan officers granted the decision. And statistically, this actually poses a challenging problem for how we can evaluate the accuracy and fairness of any risk assessment in the first place. So in particular, we have to do something about the missing data problem. We have to introduce some statistical assumptions. And typical work in this space tackles this problem by making the assumption that the missing data problem is what's known as unconfounded. That is, there is no private information. There are no unmeasured confounders that drove the decision in the first place. But as I hopefully articulated in perhaps the first 10 to 15 minutes of the talk, in these sorts of settings, that's an extremely unreasonable assumption, since past decisions were controlled by human decision makers, and these decision makers likely observed extra information that's relevant to the outcome, but not recorded in the training data that we have access to. So going back to that pretrial release setting I talked about earlier, judges may learn extenuating information about defendants during the course of the pretrial release hearing, but we don't get to see what happens behind those closed doors. In that consumer finance example, loan applicants decide whether to accept loans, but their decision to accept a loan may depend on whether they secure credit at other banks, and different banks may have access to different parts of their credit history. So more broadly, if we were to just naively ignore this sort of unmeasured confounding, this sort of private information, it would lead to vastly inaccurate risk predictions of risk in the first place and misleading evaluations of statistical risk assessments. So in this paper with my co-authors, Amanda and Edward, what we tried to do is we tried to develop a comprehensive framework for learning and evaluating counterfactual risk assessments that is robust to this sort of unmeasured confounding. So to do so, what we do in the paper is we propose what we call is a mean outcome sensitivity model as a tractable sensitivity analysis framework for these statistical risk assessment settings. So in English, what are we actually doing? In English, we ask the user to provide bounds on the extent to which unmeasured confounders could affect the outcome of interest on average. So in that pretrial release example, we simply ask the user to say how much, or the consumer finance example, how much could default rates plausibly vary between observably similar approved and rejected applicants. In that pretrial release example, we ask the user to say how much could failure to appear rates plausibly vary between observably similar released and detained defendants. Then, under those assumptions, we show that implies bounds on the magnitude of unmeasured confounding in this setting, and we also show that those sorts of statements can again be calibrated if we have access to quasi-experimental variations such as an instrument. So then this is where we start doing some statistics when we've written down the model. We show over all levels of unmeasured confounding consistent with this framework. We show we can estimate robust bounds on conditional risk given the features. We show we can translate estimated conditional risk bounds into robust recommendations. And then we develop methods to robustly evaluate predictive performance and disparities. And again, for those in this space, under the hood here is we're going to be using estimators based on a large literature and on double debiased machine learning. But we can talk about that if people are interested. And then what do we actually do with this? We were sort of motivated by practical problems of designing risk scores, so it was important to us to see that this actually works and is useful in practice. So in the last chunk of the paper, we analyze a real-world credit scoring problem from a large financial institution in Australia, Commonwealth Bank. We're using data on their own credit scores, their own proprietary credit score data. We show that varying assumptions on unmeasured confounding actually leads to drastic effects on credit scores you would produce and who gets access to credit in this setting. So we hope that this framework is actually useful in practice, and we're working with the bank to try to implement these tools in the design of credit scores. So taking a step back, what did I hopefully convince you in the last 20 minutes or so is, to me, I think econometrics can play an important role in bridging the gap between people, humans, and algorithms in these settings. In particular, using classic econometric tools of revealed preference analysis, partial identification, and causal inference, we can better evaluate the decisions that are made by humans and hopefully in turn better design algorithms to improve outcomes. But conversely, we can use these same tools to better evaluate algorithms in these settings in the first place. So I'm very excited about these questions and would love to chat more offline with folks if they're interested too. So thank you very much.
Great. Thanks, Ashesh. Any questions? Great.
There was one in the back, but.
I just wanted to ask, so it's very interesting, the second part of your project kind of discuss the categories. It seems like on the judge side as well, perhaps there's an opportunity for human algorithmic interaction somehow, and maybe justifying better decision making for the other, saying this would be the baseline score. We allow some potential discretion. Here's kind of where we think this person would be based on prior actions. I guess, is there any opportunity to?
Yeah, absolutely. So I guess concretely, what did I do in the paper is I thought about a very narrow question, which is when would we want to defer to a judge versus when would we want to automate them? I think what you're asking is the right next question is really we want a richer framework to talk about interactions between judges and statistical risk assessments. And here's where I think sort of the theme of this session becomes essential, is that to design an algorithm to do that sort of interaction requires us to take a stand on what is the human actually doing in this setting, in what ways are they biased, how might they respond to that information. So I think it's the natural next question, and the way we have to tackle it is we have to build models that can be of humans that can be taken to the data that can in turn inform that the design question in the first place. So I view that as the big question in this space. Yeah.
Great. Thanks, Ashesh.